right. So, what he said is that if sigma square phi mt if you solve this equation, you get phi m's. It is not a differential equation, but integral equation. This is equal to integral of its with some weighted function, integrate over some kernel here. Once you integrate this, whatever you get here should be equal to this. So, phi m appears in the integral as well as this. So, this is called an integral equation. So, if you solve this integral equation, you will get the phi m's. And what is important here is this kernel. And this kernel is nothing but the correlation function of the process x, for which you are trying to find the Korolevy expansion. So, the spectral density of this is known and the correlation is also known. So, this kernel is known. Once this is known, you should be able to find out the solution to this integral equation. Such solution of the integral equation give rise to a particular set of orthonormal functions, which would give rise to the beautiful property that these random variables x of n and x of m are uncorrelated. If you do not use this particular phi of m by the Korolevy expansion, you will invariably result into these xn's being correlated. And we would like to have expansions such that these are independent terms with each other, because once they are correlated, uncorrelated, each one is independent of the next one. If you do not do that, I need to take all of them together, whereas here I can take each one of them separately and then find out the response and add them up. So, this is the importance of the Korolevy expansion to find out a set of orthonormal expansions which will give rise to uncorrelated functions, uncorrelated random variables. If this happen to be white noise, then this equation is invariably satisfied, independent of whatever be the phi m, because this is equal to impulse function. So, the integral of this will be exactly equal to phi m t1 with sigma square is equal to sigma square u0 t1 minus t2 for white noise. When you integrate this, you just get exactly this, independent of whatever is the phi m. So, another property of the white noise is you expand this white noise in any orthonormal series, the coefficients you get for this will be random variables which are uncorrelated automatically. But if it is not white noise, this is not true. Only a particular set of phi n's will give you that uncorrelation property. Why is it important to us? I will pose you a problem and you see the beauty of this. A communication signal S of t is sent on a channel, and as the receiver you get a R of t which is equal to this plus white noise added to it, because invariably noise is added with the signal, and so you get a signal which is what is observed is R of t, which is actually signal embedded in white noise, additive white noise. If this noise is white, then the idea here is that if this RT is expanded in terms of orthonormal series, then each one of this problem gets transferred into a set of numbers, right. R1 is equal to S1 plus N1, which is the random variables arising out of choosing a set of orthonormal functions. The first function will give you R1 is equal to S1 plus N1. Are you with me or not? In general, I can choose any orthonormal set. Once I choose any orthonormal set, when I expand this, each one of the time function, the same orthonormal set, you get some number correspond to phi 1. So, R1 will be equal to S1 plus N1. Similarly, R2 will be equal to S2 plus N2, and so on and so forth. Since this noise is white, if this is white, and then any orthonormal function will be good enough. Now, I choose S of t as the first term in the orthonormal function. Is it possible or not? Surely, a normalized value of S of t can be used as the first term in the orthonormal series, and other terms you can generate. So, in which case all this will be, there will be no S in this. And not only that, this N1 and N2 are uncorrelated. Are you with me? Because of white noise, and this random variable is obtained by expanding it in any arbitrary orthonormal expansion, they are uncorrelated. If this is uncorrelated with this, and the signal is uncorrelated with the noise, then this has no information about the signal. So, all these are irrelevant. I only have to make a decision about the signal's presence or absence just by using only R1t. All this is because of this Coulomb-Levy expansion. And then if noise is not white, then I find the appropriate Coulomb-Levy expansion for this, and the first term of the Coulomb-Levy expansion will give rise to S plus N1. Rest of them will give you some numbers here. Hopefully, they are all basically independent of each other or uncorrelated with each other. So, in communication theory, you will see later on that the way of looking at this noise in terms of Coulomb-Levy expansion becomes very important for us to expand the received signal in terms of Coulomb-Levy expansion, so that these rest of these have become irrelevant to us. Decision is made only by looking at R1. Okay. So, we can in principle expand it in any orthonormal function, but important is to do it in terms of a specific orthonormal series, so that the random variables arising out of that are uncorrelated. The question is, how do I solve this integral equation? There is a low way, in the current low way, has done a lot of work on solving how to solve integral equations. The methods of solving integral equations. Basically, I won't go into that. The method is basically to convert this integral equation into a differential equation, and then solve the differential equation to get the solution for the integral equation. And then you will be able to find out the phis. For example, if Rx tau This is the correlation function for the random process. And then the equation you are looking for solution will be right, just substitute in the previous equation. If you solve this equation, you get solutions which are appearing to be almost like sine waves. Solution to the equation will give you phi which are cosine waves and sine waves. And the spectrum for this will be Fourier transform of this. This is called one pole spectrum. There will be one pole corresponding to this. And the Fourier transform of this is the correlation function which is given by this. So, if you solve for this phi of t, you will get the orthonormal series. And the solution of this will be cosines and sines. Only thing is they are not harmonically related sines and cosines. They are still sine waves and cosine waves, but the frequencies of these n's, because there are so many of them, phi and t, and 1 is equal to 1, 2, 3, infinity. So, all those sines and cosines will not have harmonically related frequencies if t is not infinity. If t turns to infinity, it turns out that these phi's will be harmonically related sine waves and cosine waves. And we expand this process from minus to plus infinity is almost like your Fourier series. But if t is finite, these cosines and sines will not have harmonic relationship. The frequencies are very complex relation to find out. I don't want to go into that. The method of solution of this is to write this integral as equal to minus t to t and t to minus t to t and t to t, and take a differentiation on both sides with respect to t, convert this into a differential equation, and then solve the differential equation. So, this is the Courant-Louvet expansion for any arbitrary correlation function.